GCE Advanced Level Chemistry Practical Series Experiment number 11 Identification of Anions. In this experiment, we aim to give the knowledge to identify different anions such as sulfate, sulfite, thiosulfate, sulfide, nitrate, nitrite, and carbonate. Apart from gaining the knowledge to identify these ions, we also aim to give you the knowledge to identify the presence of carbon dioxide gas and how you should be using a delivery tube when it comes to experiments such as this. Now, let's move on to identifying the reagents we will be needing for this experiment. Now, let's identify the chemicals and the equipment we'll be using for this experiment. We will be using ferrous ammonium sulfate, sodium sulfide, sodium hydroxide, sulfuric acid. Calcium hydroxide is also known as lime water. We'll be using lime water. Calcium chloride, copper sulfate, lead acetate, sodium nitrite, not nitrate, this is sodium nitrite, NaNO2, silver nitrate, potassium dichromate. You can observe the yellow color potassium dichromate here. We'll be using potassium permanganate. You can see that it is purple in color. We'll be using barium chloride. We'll be using HCl. Now, apart from these reagents, we'll be using these anion solutions that we have here. We'll take a look at the anions that we'll be using in order. We'll be using sulfate ion solutions, sulfite ion solutions, thiosulfate ion solutions, sulfide ion solutions. So, sulfide ions were formed by dissolving sodium sulfide in water, and we have covered it so that the hydrogen sulfide that may be produced will not come into this lab atmosphere, because hydrogen sulfide, as you may know, is having a very pungent smell. So therefore, we have covered it with a petri dish here. So we have sulfide ion solutions here. Then we have carbonate ion solutions, nitrate and nitrite ion solutions in these two beakers. Apart from these anions, we will be using different equipment as well. As you can see here, we have a test tube connected to a stopper, and then the stopper is attached to a delivery tube. So this setup is used to produce a gas. For example, if you take carbonate ion solutions and add to it some HCl, we'll be producing carbon dioxide. So we can use this setup to deliver the carbon dioxide with the help of this delivery tube into lime water. We'll be doing this when we are testing for carbon dioxide with the use of lime water. So this setup is used to deliver a produced gas to a specific solution or to a specific chemical species. So we'll be using this delivery tube to deliver the gas into another solution. So this setup will be used for that purpose. Apart from that, we'll be using test tubes. You can see all of the test tubes are labeled so that we can easily identify what anion solutions are present in each of these test tubes. Apart from that, we'll be using droppers. These droppers will be used to transfer small volumes of each of these solutions into our test tubes. We'll be using litmus paper. Blue and red litmus paper will be used. And we have filter paper cut into small strips here. When it comes to this experiment, we'll be using filter paper dipped in different solutions. So for that, we'll be using filter paper that is cut into small strips like this. So these are the chemicals and the equipment we will be using for this experiment. After identifying these chemicals and equipment, we can move on to the first set of experiments where we'll be looking at identifying anions or oxyanions of sulfur. Basically, we'll be looking at how to identify sulfate, sulfite, and thiosulfate ions as the oxyanions of sulfur. But apart from that, we'll be observing how to identify sulfide ions as well, S2- ions. So let's move on to that part of our experiment. In the first part of our experiment, we are going to observe how we are going to identify sulfate and sulfite ions. So we have our sulfate ions here. We are going to first use barium chloride to identify sulfite ions in a solution. So students, if you take sulfite ions into a test tube, and then to it, if you add barium chloride, to it, you are going to be observing the formation of a white color precipitate. So let's observe that. We have our sulfate ion solution, and to this sulfate ion solution, we are now going to add barium chloride. As you can see, when we add few drops of barium chloride, we can very clearly see the formation of a white color precipitate. If I shake it, I can very clearly observe that white color precipitate that was formed will spread throughout the aqueous medium and will form a suspension. Over here, what we have formed is barium sulfate. Barium sulfate is water insoluble. So therefore, you can observe this white precipitate dispersed throughout the aqueous medium, and you can observe this aqueous medium is now white in color. That is due to the barium sulfate precipitate that is formed, that is dispersed throughout the aqueous medium. Now, let's take a small portion of sulfite ions, SO3 2- ions. So we have a test tube labeled sulfite ions. Now we have taken sulfite ions into this test tube. To it, let's add a small amount of barium chloride. And you are going to observe, as we add barium chloride to sulfite ions as well, we are forming a white color precipitate. This white color precipitate was formed due to formation of barium sulfite. Barium sulfite. So barium sulfite is a water insoluble precipitate, just like barium sulfate. So let's compare it side by side. You can observe barium sulfate over here. You can see a white color precipitate was formed when we add barium 2+ ions to the sulfate ion solution, and when we added barium 2+ ions to sulfite ion solution also, we can see the formation of a white color precipitate, which is barium sulfite. So barium sulfate and barium sulfite both are water insoluble white color precipitates. Now students, we can move on to adding a little bit of HCl to each of these precipitates we have formed here to observe whether these precipitates get dissolved in the presence of HCl. So let's keep our barium chloride aside. And let's take the HCl that we have over here. And now let's move on to our barium sulfide suspension we have here. So this particular suspension contains a lot of barium sulfide. To observe a very clear dissolving of barium sulfide, we'll take a small amount of the suspension into another test tube. Now we have taken a small amount of barium sulfide suspension into another test tube here, and we are going to be adding HCl directly to it. You can see how this suspension dissolves in HCl. You can see as I add HCl how the color decreases little by little. If I shake it, you'll be able to see it a bit more clearly. Let's add a bit more HCl. You can see as the HCl droplets enter the medium, you can observe how the color of the solution is decreasing. Can you see as the HCl enters the medium, it is starting to dissolve. Now students, we have observed that the barium sulfide is dissolving in HCl, but we still have quite a lot of barium sulfide left in this suspension. So we can dilute it a little further so that we can observe the formation of a clear solution when added with HCl. Now as you can see students, after adding a few drops of HCl to a diluted suspension of barium sulfide, we saw that barium sulfide completely dissolved in HCl. So this indicates, unlike barium sulfate, barium sulfide dissolves in HCl. So just for a comparison, when we took barium sulfate and added HCl to it, barium sulfate did not dissolve in HCl. However, when you took a barium sulfide sample and added HCl to it, we were able to dissolve it completely to form a clear solution like this. So this indicates that barium sulfide is soluble in HCl. Barium sulfide is soluble in HCl, however, barium sulfate is not going to dissolve in HCl. Now let's move on to the next step of this experiment. Now, in this part of our experiment, students, we are going to observe how a solid sample containing sulfide ions react with HCl. So we have sodium sulfide here, and we are going to add to it a small amount of hydrochloric acid. And as they react, it will release sulfur dioxide gas, and you can very clearly observe the formation of sulfur dioxide gas through the pungent smell that sulfur dioxide gas has. You should not be inhaling this, it's an irritant gas. So you should be conducting this experiment in a fume hood or a well ventilated area. So sulfur dioxide, when it comes into contact with acidified potassium dichromate or acidified potassium permanganate, both of which are good oxidizing agents. So when sulfur dioxide come into contact with these oxidizing agents, sulfur dioxide will get oxidized to form sulfate ions, and these oxidizing agents will get reduced. So as these oxidizing agents get reduced, they will give us a color change. So we are going to observe the color changes that are given when we use acidified potassium permanganate as the oxidizing agent, and when we use potassium permanganate as the oxidizing agent as well. So let's first get our oxidizing agents prepared. So potassium dichromate that we have over here is just an aqueous solution of K2Cr2O7 or potassium dichromate. You can observe that it's a orange color solution. We have to first acidify our potassium dichromate solution. So let's take a test tube and acidify our potassium dichromate solution. Let's transfer a small volume of potassium dichromate into our test tube here. So we have transferred a small volume of potassium dichromate into our test tube. You can observe the color very clearly. Potassium dichromate is an orange color solution, and to this we can add dilute sulfuric acid. Let's add a small amount of dilute sulfuric acid. Now we have prepared our acidified potassium dichromate solution. Similarly, we will now move on to preparing our acidified potassium permanganate solution. In order to do that, we'll take another test tube, and we have our potassium permanganate solution here. You can observe that it is purple in color. Now let's take a small volume of potassium permanganate into our test tube. And then we are going to acidify this potassium permanganate solution by adding sulfuric acid. So we have our sulfuric acid here. Let's add a small volume of sulfuric acid to acidify our potassium permanganate solution. So we have now prepared our acidified potassium permanganate solution as well. So on my left, the orange color solution that you observe is our acidified potassium dichromate solution, and on my right, the purple color solution is our acidified potassium permanganate solution. Now, after preparing our acidified potassium dichromate and acidified potassium permanganate solutions, we can move on to taking a solid sample of sodium sulfite into our test tube here. You can see we have labeled this test tube sulfite ions. That is because we'll be taking solid sodium sulfite which contains sulfite ions. And we are going to add hydrochloric acid to this sodium sulfite solid. This is going to release sulfur dioxide gas, which is a pungent gas. Sulfur dioxide gas, when it comes into contact with acidified potassium dichromate, sulfur dioxide gets oxidized to sulfate ions, while the dichromate ions get reduced to chromium 3 plus, which results in forming a green color solution. So when we send sulfur dioxide gas through acidified potassium dichromate, you can observe the color change of this solution from orange to green. And if you send sulfur dioxide gas through acidified potassium permanganate, you are going to observe the color of the acidified potassium permanganate changing from purple to colorless. As sulfur dioxide gets oxidized to sulfate ions, acidified potassium permanganate or permanganate ions that are purple in color get reduced to form Mn2 plus, which is observed as a colorless solution. Now, to make this observation very clear, we are first going to dilute this solution a little further so we can observe this color change a bit clearer. So we will take another test tube and transfer a small amount of this solution to that test tube, and we will add water to dilute it further. Similarly, we will dilute acidified potassium permanganate solution as well. We have our acidified potassium permanganate solution here. We will take another test tube and transfer a small amount of acidified potassium permanganate to that test tube. And we will add distilled water and we will dilute this solution a bit further. After diluting these two oxidizing agents, we can now take a sample of sodium sulfite into our test tube and add it with HCl. To make this reaction happen a little faster, we can use a spirit burner and heat up the reaction mixture so that it produces sulfur dioxide gas a little faster than it would when we conduct this experiment without heating it up. So we have this test tube that we spoke of earlier. To this, we will be taking a small solid sample of sodium sulfite. We'll be taking sodium sulfite. You can see it's a white color solid. After taking a little bit of sodium sulfite into this test tube, we are going to be ready with a delivery tube with the rubber stopper attached to it, so that as soon as we add HCl to this test tube, we can connect the rubber stopper and the produced sulfur dioxide gas will be delivered through this delivery tube into the acidified potassium dichromate solution, and after we observe the color change, we can move into acidified potassium permanganate solution. So we can easily use this delivery tube to introduce the sulfur dioxide gas that is produced into each of these oxidizing agents. So we are going to be using this rubber stopper connected to the delivery tube to make sure the sulfur dioxide produced here gets delivered directly into the solutions we wanted to introduce sulfur dioxide to. So we'll keep our delivery tube ready. In fact, we can place the open end of the delivery tube in our acidified potassium dichromate solution like so, and then we can keep the rubber stopper aside for the time being, and then we can take our HCl that we have over here and add a small volume of HCl into this sodium sulfite solid that we have here. So as soon as we add it, we are going to close it with this rubber stopper. You can see a gas was produced, and that produced gas is now sent through the acidified potassium dichromate solution. We can continue to add a bit more hydrochloric acid, so we will take the same dropper and we will add a small amount of HCl and quickly close the rubber stopper. If sulfur dioxide is not getting produced fast enough, we can always heat this setup with the use of a spirit burner. You can see as we heat it, more and more sulfur dioxide gas is produced. As you can see, students, when we send the sulfur dioxide gas, the color gradually starts to change, and we can see it is now green in color. So this green color observation indicates that the dichromate has turned into chromium 3 plus ions. So let me remove the setup and show you the observation very clearly. You can see we initially started with an orange color dichromate solution, but after we sent sulfur dioxide through it, the dichromate solution turned into a chromium 3 plus ion solution, or dichromate ion got reduced into chromium 3 plus, and chromium 3 plus ions in aqueous medium will form a complex with sulfate ions and water, which is green in color. That is why we observe this green color solution here. And as dichromate got reduced, the sulfur dioxide got oxidized to form sulfate ions. Sulfur dioxide got oxidized to form sulfate, and dichromate reduced to form chromium 3 plus ions, and that is why we observe this green color solution. So now, students, we can move on to acidified potassium permanganate. So acidified potassium permanganate is purple in color. Let's send sulfur dioxide gas through it. So we have already added the two reagents together. We can heat up the mixture again once more, and you will observe that the potassium dichromate solution will also change color. In this case, the purple color will turn colorless. So before using the delivery tube again, we will wipe the delivery tube as it was introduced into our potassium dichromate solution earlier. Now, after wiping it clean, we can introduce it into acidified potassium permanganate solution. And now let's heat up the mixture. Did you observe the color change, students? I hope you did, because we can now see that when we send sulfur dioxide gas that was produced through acidified potassium permanganate solution, which was purple in color, it has turned to a colorless solution. So we can very clearly observe that when sulfur dioxide is reacted with acidified potassium permanganate, it gets reduced to form Mn2 plus ions. And Mn2 plus ions in aqueous medium is going to appear colorless, although Mn2 plus aqueous ions are going to form a complex which is pink in color or pale pink in color. This color intensity is very low. We will not observe that color. Instead, we are going to observe the formation of a colorless solution. So permanganate ions that are purple in color got reduced to form Mn2 plus, and that is why we can see a colorless solution here. And sulfur dioxide got oxidized to form sulfate ions. So this is a very clear observation that when we add HCl to a solid sample of sulfite ions or to a solid ionic compound that contains sulfite ions, they will react with HCl to produce sulfur dioxide. We took sodium sulfite here. So when we took sodium sulfite and reacted it with hydrochloric acid, sulfur dioxide gas was produced. And to identify the sulfur dioxide gas that is produced, we can send the sulfur dioxide gas through acidified potassium dichromate. And we observed when we send it through acidified potassium dichromate, the orange color dichromate solution turned into a green color chromium 3 plus aqueous ion solution. And when we send sulfur dioxide through potassium permanganate solution, which is purple in color, we saw it changed color to a colorless solution. So this indicates the presence of sulfur dioxide ion. So you can identify the presence of sulfite ions through addition of HCl and send in the gas that is produced through an oxidizing agent such as acidified potassium dichromate or acidified potassium permanganate. Now, let's move on to the next part of this experiment. Now, we will be taking a look at how sulfide ions can be identified with different reactions. So, first, we are going to take our sulfide ion solution. We have prepared this sulfide aqueous ion solution with the use of sodium sulfide. So we have taken sodium sulfide solid and dissolved it in distilled water. And now we are going to take sodium sulfide aqueous solution that we have in front of us here and react it with copper sulfate and silver nitrate. So when copper 2 plus ions comes into contact with sulfide ions, they form copper sulfide, or more accurately, cupric sulfide. Cupric sulfide is going to be black color, water insoluble precipitate. So you will observe the formation of a black color water insoluble precipitate formed when we introduce Cu2 plus ions into our sulfide ion solution, S2 minus ion solution. And then we will see how silver 1 plus ions react with sulfide ions. So as silver 1 plus ions comes into contact with sulfide ions, you will observe the formation of a black color precipitate. This is again because silver sulfide that is getting formed is a water insoluble black color precipitate. So now let's observe these reactions. So we have here our sulfide ion solution. Let's take small sample of the sulfide ion solution into 2 test tubes. So we have taken it into two different test tubes, and to one test tube we will be adding copper sulfate, and to the other we'll be adding silver nitrate. Now copper sulfate contains Cu2 plus ions, and our sulfide aqueous ion solutions contain S2 minus aqueous ions. So Cu2 plus and S2 minus together will form cupric sulfide, which is a black color water insoluble precipitate. So let's observe that. So let's take a small amount of copper sulfate and we can add it to our sulfide ion solution we have here. Observe what happens when sulfide ions come into contact with Cu2 plus ions. Did you observe the formation of a black color precipitate? If I shake it, you can see that it gets dispersed throughout the medium. I can add a little bit more copper sulfate to give you a very clear color change. So now you can see very clearly what we have formed here is a black color precipitate, and the black color cupric sulfide precipitate is now dispersed throughout this aqueous medium and has formed a suspension. If you allow it to stand for a while, you will see the black color cupric sulfide precipitate will collect at the bottom, and you can very clearly observe the black color precipitate. So what we have formed here is cupric sulfide, which is a black color water insoluble precipitate. So this test can be used to identify the presence of sulfide ions. Now we can move on to adding silver 1 plus ions into our sulfide ion aqueous medium. So in a silver nitrate solution we have silver 1 plus ions. So if you take this silver nitrate solution, since it contains silver 1 plus ions, if you add it to our sulfide ion solution, you will observe the formation of a black color precipitate yet again. So let's take a dropper and add a few drops of silver nitrate. You can see as silver nitrate is added to this sulfide ion solution, we started forming a black color precipitate here. And this black color precipitate that is formed is silver sulfide, Ag2S. So silver sulfide is going to be again a black color precipitate that is water insoluble. We can mix it really well. You can see this black color precipitate gets dispersed, and if you add a few more drops of silver 1 plus ions, you can observe the black color precipitate that is formed very clearly here. You can see some black color precipitate particles coating the walls of this test tube as well, and black color silver sulfide precipitate will after a while get collected at the bottom of the test tube. So students, we observed when silver ions come into contact with sulfide ions, we form silver sulfide, a black color water insoluble precipitate. Or if you introduce cupric ions or Cu2 plus ions into a sulfide ion solution, we saw the formation of cupric sulfide, which is also a black color precipitate. So this, you can see the black color precipitate is now starting to get collected at the bottom we have produced a black color cupric sulfide precipitate here. So what you see here is a black color cupric sulfide precipitate. And then on this test tube we have silver reacted with sulfide ions, and what you see over here is also the formation of black color silver sulfide precipitate, which is water insoluble and black in color. So you can use these two tests to identify the presence of sulfide ions in an aqueous medium. If sulfide ions are present in an aqueous medium, you can identify that by the addition of either copper sulfate or silver nitrate. With both of these solutions, you will observe the formation of a black color precipitate. It's going to be, if you add copper sulfate, they are going to form copper sulfide or cupric sulfide, and if you add silver nitrate, you will see the formation of silver sulfide, which is a black color precipitate. Now let's move on to the next part of this experiment. Now we are going to take a look at another experiment that can be used to identify the presence of sulfide ions. So for this experiment, we are going to take solid sodium sulfide. So if you take a small amount of solid sodium sulfide and react it with HCl, you're going to see formation of hydrogen sulfide. Now students, hydrogen sulfide is a irritant gas. You should not be inhaling it. If you inhale it in moderate conditions, it could lead to nausea, vomiting as well. So you should not be inhaling this. It is less toxic compared to sulfur dioxide. Sulfur dioxide is severely irritating and it is toxic. You should not be inhaling sulfur dioxide because it is quite toxic. However, when it comes to hydrogen sulfide, it is not as toxic as sulfur dioxide, but still it is going to be a irritating gas. Hydrogen sulfide has a very characteristic smell of rotten eggs. So you can very clearly identify that hydrogen sulfide is formed by its smell. It smells exactly like rotten eggs. So students, now we can move on to adding a small amount of sodium sulfide into a test tube, and we will be adding hydrochloric acid to that test tube, and it will produce hydrogen sulfide gas. And with the help of a delivery tube, we are going to introduce this hydrogen sulfide onto a piece of filter paper that is soaked in lead acetate. So we have our lead acetate here. We are going to take a small amount of lead acetate into a petri dish and we are going to soak it in a filter paper. And after that, when hydrogen sulfide gas is produced, we are going to introduce the hydrogen sulfide gas onto the filter paper that is soaked with lead acetate. So let's move on to conducting this experiment. Now let's take our sodium sulfide. You can see sodium sulfide is a yellow-orange color solid. We have taken some sodium sulfide, solid sodium sulfide here, and we are going to leave it aside for the time being. Afterwards, we will take small amount of lead acetate. We can pour a small amount of lead acetate onto a petri dish here. We can After taking a small amount of lead acetate onto a petri dish, we can now move on to soaking a small piece of filter paper in lead acetate. Now, all that is left for us to do is add the HCl to our sodium sulfide that we have here. And as soon as we add it, we are going to place the stopper and direct all the hydrogen sulfide that is produced through this delivery tube onto our filter paper soaked with lead acetate. Now, let's move on to that step. We are going to be adding HCl. As soon as we add HCl, we are going to place the stopper. And now we are going to take our filter paper soaked in lead acetate. You will observe as we send the hydrogen sulfide gas, this paper soaked in lead acetate turn to a black color. This is because the produced hydrogen sulfide gas, when it comes into contact with lead acetate, it forms lead sulfide, which is a black color precipitate. And over here you can see that it has turned black when we introduce hydrogen sulfide to this filter paper soaked with lead acetate. So students, this is the observation that we were aiming to obtain. If you want to observe it again, we can soak another piece of filter paper and add some HCl, and then we can see how the color changes as hydrogen sulfide comes into contact with lead acetate. Do you observe here how the color changes when the hydrogen sulfide gas is coming into contact with lead acetate? Very clearly we can see when hydrogen sulfide comes into contact with lead acetate, it forms lead sulfide, which is going to be a black color precipitate, and that is why the filter papers soaked in lead acetate turn to a black color. So this color is observed due to the lead acetate turning into lead sulfide, which is a black color precipitate. Now students, let's remove this setup from over here, because we have now produced hydrogen gas. Because now we have produced hydrogen sulfide gas, it is not a gas that you should be inhaling. So therefore, let's remove this setup and move on to our next step. Now students, we are going to observe how we can identify the presence of sulfide ions with another reaction. That is, we learned in the previous reaction, when sodium sulfide or any group 1, group 2 sulfides, when they are reacted with hydrochloric acid, we know it produces hydrogen sulfide, which is a gas that has rotten egg smell. So this hydrogen sulfide gas, if it is sent through acidified potassium dichromate, we have it here. We have 2 vials to keep one as a control. So we have acidified potassium dichromate here. We observe the color of the acidified potassium dichromate, which is orange. So if we send hydrogen sulfide through it, you will observe the color of this acidified potassium dichromate changes from orange to a green color. As this color change happens, you will observe that hydrogen sulfide actually gets oxidized to form sulfur. It is getting formed in the form of colloidal sulfur. So you will observe that the solution is becoming milky. So the orange color turns to a green color, as well as solution turns milky. So you will be forming a very cloudy suspension that is a mix of chromium 3 plus green color solution, and the colloidal sulfur that is formed here will be present in the aqueous medium dispersed, which will cause the solution to be a bit more unclear and will have a little green color to it as well due to the formation of chromium 3 plus ions here. So what happens in this reaction is dichromate ions will get reduced to chromium 3 plus ions, which will turn the solution to a green color, and hydrogen sulfide or the sulfide ions get oxidized to form sulfur. So therefore the solution will turn milky due to sulfur being formed in the form of colloidal sulfur, which is going to be dispersed throughout the aqueous medium, forming a milky solution. So milky solution mixed with a green color solution together will form a very unclear milky solution. So that is what is going to happen when we send hydrogen sulfide through the acidified potassium dichromate. When we send it through acidified potassium permanganate that we have here. Now potassium permanganate, acidified potassium permanganate is purple in color. We have another vial for comparison. So when we send hydrogen sulfide through acidified potassium permanganate, you will see the purple color will disappear. This is because as hydrogen sulfide get oxidized to form sulfur, potassium permanganate or the purple color permanganate ion get reduced to form Mn2 plus, which is a colorless solution. So the solution will become clear and colorless. As this reaction takes place, hydrogen sulfide will produce colloidal sulfur, which will make the solution milky. So you're going to observe the formation of a milky solution here, which doesn't have a color. It's going to be basically a milky solution due to the formation of colloidal sulfur or due to the formation of solid sulfur. So let's go ahead and observe these reactions. So let's first take a small amount of sodium sulfide into this test tube. We have our sodium sulfide here. We will take a small sample of sodium sulfide into our test tube over here. Now students, you can observe we have taken a yellow color sodium sulfide solid into this test tube, and we are going to add hydrochloric acid to this test tube, and as soon as we add the hydrochloric acid, we will place the rubber stopper and direct all the hydrogen sulfide gas that is produced into this acidified potassium dichromate solution. So since we are going to start in that manner, we can insert this delivery tube inside our acidified potassium dichromate solution, and now we are going to add HCl to this sodium sulfide. So as soon as we add HCl, we will be placing the rubber stopper. You can observe the color is changing in the acidified potassium dichromate solution. Can you observe that as the color turned to a green color, the solution became unclear? This is because as potassium dichromate as potassium dichromate turned into chromium 3 plus aqueous ion solution, sulfur, solid sulfur, was formed in the form of colloidal sulfur, and that is why we have now formed an unclear solution due to the presence of colloidal sulfur. So you can see the orange color dichromate ion solution turned into a green color solution, but this green color solution is mixed with sulfur. That's why we have this unclear green color solution. So the cloudiness in the green color solution is due to the presence of colloidal sulfur. Now let's insert this delivery tube. After cleaning it, let's insert this delivery tube into our acidified potassium permanganate solution, and let's add a little bit of HCl. Can you observe the color of HCl? Can you observe the color of the acidified potassium permanganate solution gradually decreases? We can add a little bit more HCl to our tube here. Now students, we can very clearly see that the color of acidified potassium permanganate solution completely disappeared, and now we have formed a milky solution. So what is the reason for this milky nature in the solution? That is due to the formation of colloidal sulfur. So if you compare the acidified potassium permanganate solution that we have on the left, which is purple in color, to the milky color solution that we have on the right, we can observe that permanganate ions got reduced to form Mn2+, which are colorless in solution. We can observe the permanganate ions that are purple in color turned into Mn2+, which are colorless, and as this reduction happens, hydrogen sulfide got oxidized to form sulfur, solid sulfur in the form of colloidal sulfur, and that is why we can observe this milky color or milky nature in this clear solution that we have formed here. So that is why we can observe this milky nature in the solution over here. This is due to solid sulfur being suspended throughout the aqueous medium. So students, now we have observed what happens when hydrogen sulfide is sent through acidified potassium permanganate and acidified potassium dichromate. Let's remove this sample here from the lab as it is still producing hydrogen sulfide, and we will come to discuss the color changes further after that. Students, let's go through the summary of the identification tests that we carried out for sulfide ions. At the beginning of this experiment, we reacted a sulfide ion solution with silver nitrate and with copper sulfate. We saw when copper 2+ ions come into contact with sulfide ions, it formed copper sulfide, which is a black color water insoluble precipitate. So this reaction can be used to identify the presence of sulfide ions. If not, we can add silver nitrate. When silver plus ions come into contact with sulfide ions, it forms silver sulfide, which is also a black color water insoluble precipitate. After that, we moved on to reacting a solid sodium sulfide sample with hydrochloric acid. When we added hydrochloric acid to sodium sulfide, we observed the formation of a pungent smelling gas, and this gas is hydrogen sulfide. Hydrogen sulfide is an irritant gas and it has a very characteristic smell of rotten eggs. So the formation of hydrogen sulfide is a confirmation for the presence of sulfide ions. However, you can further identify that hydrogen sulfide has been formed by taking a filter paper and dipping the filter paper in lead acetate, and if you expose this filter paper that is dipped in lead acetate to the hydrogen sulfide gas that is produced, we observed that there is a black color shiny precipitate that is formed, which is lead sulfide. So lead sulfide was formed when the hydrogen sulfide gas came into contact with the lead acetate that was present on the filter paper. So this was another experiment that we could use to identify the presence of sulfide ions. Apart from that, we can take sodium sulfide solid sample and react it with hydrochloric acid to produce hydrogen sulfide again. And this produced hydrogen sulfide, if it is sent through an oxidizing agent such as acidified potassium permanganate, we observed potassium permanganate purple color solution turned colorless. This is because as potassium permanganate gets reduced to form Mn2+, it loses its color. Potassium permanganate is purple in color, and as it reduces, it forms Mn2+, which is a colorless solution. So as purple color turned colorless, we also observed hydrogen sulfide got oxidized to form sulfur in the form of colloidal sulfur, or solid sulfur was formed when we sent hydrogen sulfide through acidified potassium permanganate. So therefore, due to the formation of this solid sulfur, we saw the solution turning milky. The solid sulfur that is formed was dispersed throughout the aqueous medium and turned this colorless Mn2+ aqueous solution milky. When you send hydrogen sulfide gas through another oxidizing agent such as acidified dichromate ions, we saw the orange color of the dichromate ions first change to a green color, and afterwards we will observe that the solution is starting to turn a bit unclear or cloudy. So solution becomes unclear or cloudy due to the formation of colloidal sulfur as hydrogen sulfide gets oxidized to form sulfur. And as this reaction takes place, we observed that orange color dichromate ions turning into chromium 3+ aqueous ions, which happen to have a green color to it. So students, these are the identification tests that we used to identify the presence of sulfide ions along with their observations. Now let's move on to thiosulfate ion. Now students, we are going to be looking at the identification test for the thiosulfate ion solutions. We have our thiosulfate ion solution here, and we are going to take a small volume of the thiosulfate ion solution to a test tube labeled thiosulfate so that we can very clearly identify which test tubes are containing thiosulfate. We have a clear solution of thiosulfate ion solution here, and to this we will be adding hydrochloric acid, HCl. And with the help of a dropper, we can add a small amount of HCl to our solution that we have here. We can see as soon as we add it, we can see the formation of a white color solid here. So when we add HCl, to a thiosulfate ion solution, we can see the solution is starting to become milky. This is due to thiosulfate ions reacting with hydrochloric acid to produce sulfur and sulfur dioxide. So sulfur dioxide that is produced is removed from this system. However, the sulfur that is produced here is going to be present as colloidal sulfur, or you commonly know this as sulfur solid. So sulfur solid is produced here, and you can see it has a bit of a yellowish color, and this observation proves that in the solution that we initially took to our test tube, there were thiosulfate ions. If you mix it, you can very clearly see the yellowish precipitate, or we can see there is quite a lot of colloidal sulfur formed here, and now the solution is completely filled with solid sulfur that is produced, and it is dispersed throughout the aqueous medium. So therefore we can observe the yellow color very clearly. So solid sulfur, when it is produced in very small quantities, it is just going to turn the solution milky, because the amount of solid sulfur that is produced is very little. However, if you have produced quite a lot of solid sulfur or colloidal sulfur, you are going to observe a yellow color here. So this is the observation. When you add hydrochloric acid to thiosulfate solution, you get sulfur solid and sulfur dioxide as a result. And what you observe here is a sulfur solid that is produced, which has a yellow color to it. Now we will set it aside for a while and observe whether sulfur dioxide is actually getting produced when we add HCl to our thiosulfate ion solutions. To observe this, we will take another test tube and take a sample of thiosulfate ions into this test tube, and then before we add HCl to this, we will be taking a delivery tube and we will insert the other end of a delivery tube inside a acidified potassium permanganate solution. Now we initially observed when sulfur dioxide gas is bubbled through an acidified potassium permanganate solution, we observed the color of the potassium permanganate solution disappears. This is because the sulfur dioxide will get oxidized to form sulfate ions, and permanganate ions that are purple in color will get reduced to form Mn2 plus ions, which are colorless. So that is why the purple color solution will become colorless, and sulfur dioxide will get oxidized to sulfate ions. To make this reaction happen a little faster, we can use a spirit burner and heat up the entire mixture as well. So let's prepare for that first. We'll light up the spirit burner, and then we'll initially add a little bit of HCl into this thiosulfate solution and send the gas produced through our acidified potassium permanganate solution. Both of these test tubes contain acidified potassium permanganate solutions. One is going to be kept as a control, while the other is going to be used for this experiment. We will insert one end of delivery tube into the acidified potassium permanganate solution, and we'll place the rubber stopper on the test tube as soon as we add the HCl onto our thiosulfate solution. to speed this reaction up, we can heat this mixture. As you can see, students, as we send sulfur dioxide through the acidified potassium permanganate solution, we can very clearly see the acidified potassium permanganate solution becomes colorless gradually. So now the acidified potassium permanganate solution is less purple compared to the control that we have right next to it. Gradually it loses its color. Now, students, you can very clearly see the color of this solution has completely turned colorless. You can very clearly see the color of the solution has completely turned colorless. If you observe the color of the potassium permanganate before we sent sulfur dioxide through it and after, you can very clearly observe that the purple color of the potassium permanganate solution has completely disappeared because it has gotten reduced to form Mn2+. Permanganate ions, which are purple in color, turned into Mn2+, which are going to appear colorless in aqueous medium. And as this happened, sulfur dioxide turned into sulfate ions. Now, students, let's send sulfur dioxide through an acidified potassium dichromate solution. So we will use the same setup. And we will gently heat it until we can observe a color change in our acidified potassium dichromate solution. You can see acidified potassium dichromate solution gradually turns to a green color. We are heating this reaction mixture up to make the reaction happen a bit faster so that we can see sulfur dioxide being produced a bit faster, and we can observe the color change a little faster than when you normally would. We are heating up the solution to observe the color change a little faster. You can see the color of the acidified potassium permanganate solution is gradually changing. Now, students, you can observe that the acidified potassium dichromate solution, earlier it was orange in color, but after we sent sulfur dioxide gas through it, it has now turned to a green color. So acidified potassium dichromate earlier on was orange in color. This is due to the presence of dichromate ions. Dichromate ions are orange in color. And as the dichromate ions undergo a reduction, they turn into chromium 3+ ions. Chromium 3+ ions in aqueous medium appear green in color. You can observe here, this solution is green in color due to the presence of chromium 3+ ions in aqueous medium. So what has happened to the sulfur dioxide that was sent through acidified potassium dichromate? Sulfur dioxide got oxidized to sulfate. Sulfur dioxide got oxidized to form sulfate, and dichromate got reduced to form chromium 3 plus. And these are the color changes that you will observe when you send sulfur dioxide that is produced when you react thiosulfate ions with hydrochloric acid through acidified potassium dichromate solution. So, when you add hydrochloric acid to an aqueous solution of thiosulfate ions, they will react with hydrochloric acid to form sulfur or sulfur solid and sulfur dioxide. Sulfur solid will be formed in the form of colloidal sulfur. Apart from solid sulfur, we will be forming sulfur dioxide. And formation of sulfur is very clear through this yellow color precipitate. So we can see a yellow color precipitate is readily formed when we add hydrochloric acid to a thiosulfate ion solution. So this confirms the presence of solid sulfur in the medium. To confirm the presence of sulfur dioxide, we can send sulfur dioxide through acidified potassium permanganate or acidified potassium dichromate solution. And when we send sulfur dioxide through acidified potassium permanganate, we observe the purple color of the acidified potassium permanganate solution completely disappears to produce a colorless solution. When we send sulfur dioxide through acidified potassium dichromate orange color solution, we formed a green color chromium 3 plus ion solution due to dichromate ions reducing while sulfur dioxide oxidizing to sulfate ions. Now students, these tests are the tests that can be used to identify the presence of thiosulfate ions in an aqueous medium. Now let's move on to the next test. Students, in the very first part of the identification test that we conducted for the thiosulfate ions, we added hydrochloric acid to our thiosulfate ion solution and we produced sulfur along with sulfur dioxide. And at that point, sulfur was dispersed throughout the medium and we couldn't clearly observe the color. And now it has been about 10 to 15 minutes and you can observe the sulfur has now gotten collected at the bottom of the test tube, and we can very clearly see a yellow color precipitate that is present here due to solid sulfur getting collected at the bottom of the test tube. So observe what has happened after we allowed it to sit for a while on our test tube rack here, and we can very clearly see the tiny solid sulfur particles that were produced were getting collected at the bottom, and we can clearly observe the yellow color that is seen here. So with that, we can move on to the next test that we can use to identify the presence of thiosulfate ions. Now everyone, we are going to observe how the thiosulfate ion solutions will react with silver plus ions and lead 2 plus ion solutions. So to obtain lead 2 plus ion solutions, we have lead acetate, and to obtain our silver 1 plus ions, we have silver nitrate. So to observe how these ions react with the thiosulfate ion, we will mix sodium thiosulfate with silver nitrate to observe what changes take place when we mix these two solutions. So let's take a small amount of thiosulfate ions we have here. So we are taking a small volume of thiosulfate ion solution into a test tube, and to this we will be adding a small volume of silver nitrate. Now students, before I add silver nitrate into this test tube, let me tell you the reaction that is actually taking place here. Silver ions will come into contact with the thiosulfate ion and will form silver thiosulfate. Silver thiosulfate is unstable, so it decomposes readily to form silver sulfide. And as you saw earlier, silver sulfide is a black color precipitate, and as it turns into silver sulfide, you will observe a little bit of a brown color in the medium as well. However, the final product that is going to be formed is silver sulfide, which is black in color and it is water insoluble. So we'll observe silver sulfide getting collected at the bottom of the test tube. So initially, a white color precipitate, silver thiosulfate, will be formed, which is unstable. It readily turns into silver sulfide. So as I introduce silver nitrate to this test tube, now students, let's observe what happens when we add silver nitrate. Did you see, as soon as silver nitrate was added, a white color precipitate was formed, and as you can see, little by little, the white color precipitate is changing color to brown and then to black. So you can see the white color precipitate is now a black color precipitate. So as soon as we added silver, we saw the formation of silver thiosulfate. As silver thiosulfate is unstable, it decomposes to form silver sulfide, which is a black precipitate. As you can see over here at the bottom of the test tube, we can see a black precipitate that is formed. Let's observe that one more time. So as soon as we take a small amount of silver nitrate, and if you add silver nitrate now, you will see the formation of a white color precipitate first. And that white color precipitate gradually changes its color and turns into a brown color precipitate and to a black color precipitate. As it turns into silver sulfide, it for a while appears brown, but after it completely turns into silver sulfide, it will be very clearly a black color precipitate that is formed at the bottom of the test tube here. So students, this indicates the presence of thiosulfate ions. This is a good test that you can use to identify the presence of thiosulfate ions. As silver ions are added to a thiosulfate ion solution, initially a white color precipitate will be observed, but almost immediately this white color precipitate will start changing its color and it will form black color silver sulfide precipitate. So you can see at the back of this test tube, silver sulfide, black color precipitate is formed. Now let's do a similar experiment with lead acetate. First of all, let's take a small amount of thiosulfate ions or thiosulfate ion solution into our test tube here, and then we can add a small volume of lead acetate into this test tube. So you will see, as lead acetate is added, a white color precipitate will be formed. However, this precipitate will not immediately turn into a black color. Lead thiosulfate is a stable precipitate. Lead thiosulfate will be white and it will not get converted into lead sulfide as we observe. It will not readily get converted into lead sulfide. If you want to convert it into lead sulfide, you can heat it up, and as you heat up this precipitate, you will see the white color lead thiosulfate turns into lead sulfide, which is a black color precipitate. However, as soon as you add lead acetate into our thiosulfate ion solution, the white color precipitate that is formed will not turn into a black color precipitate readily. So let's add our lead acetate into our thiosulfate solution. As you can see, when we add lead acetate to our thiosulfate solution, we can very clearly observe the formation of a white precipitate. We can add a little bit more. Let's add a little bit more lead acetate. You can see when lead acetate comes into contact with the thiosulfate solution, we form lead thiosulfate, which is a white color precipitate. Does it change its color like silver thiosulfate did? No. Silver thiosulfate readily turned into silver sulfide, but lead thiosulfate, which is a white color precipitate, does not decompose to form lead sulfide readily. When you heat this reaction mixture, you can see the lead thiosulfate turning into lead sulfide, forming a black color precipitate. So let's move on to that. We can actually first of all mix this really well. When you mix it, you can see the precipitate gets dispersed further. Now students, we have mixed the solution. You can see the precipitate is now dispersed throughout this aqueous medium. Now students, we observed that when lead acetate was added with sodium thiosulfate or thiosulfate ion solutions, we saw the formation of lead thiosulfate, which is a white color precipitate. It was a stable precipitate. It did not undergo decomposition to produce lead sulfide. It did not undergo decomposition. So therefore, the precipitate that you observe here now, which is sinking to the bottom, is lead thiosulfate. If you heat this reaction mixture, you will observe that this white color lead thiosulfate will turn into a black color precipitate, which is lead sulfide. Let's observe that reaction. Now we have our spirit burner set up here and it is lit. We are now going to heat this lead thiosulfate precipitate and observe the color change. Remember students, we started with a white color precipitate. So let's observe what happens to the white color precipitate here. We can clearly see the white color of the precipitate is decreasing little by little. It is now a little bit of a grayish color. Now you can observe the precipitate is a bit of a darker gray color. It is no longer white. We can observe that it is no longer white in color. So as we heat it up, you can very clearly see that it is undergoing a change from white to a black color. Currently, it is a darker gray color, as I mentioned earlier. As the water gets boiled, you can see the suspension is getting mixed with the aqueous solution, and you can very clearly observe the color of the precipitate as the suspension is getting mixed. So the color of the precipitate is no longer white. It is now more towards a black color. Now, students, you can very clearly observe there is a dark gray precipitate here. That is because majority of it is now turned into lead sulfide, which is a black color precipitate. If you keep on heating this, you can see very clearly the color gets darker and darker and moves towards a black color, and once all of the lead thiosulfate is converted into lead sulfide, you will observe a black color precipitate. Right now, what you observe here is a dark gray color precipitate. You can very clearly observe it as I bring this test tube to our spirit burner here. As the precipitate gets mixed in the aqueous medium, you can see the very nice gray color that we observe here. So pay attention to this area. You can see how it is starting to get mixed. So you can observe the dark gray color of the precipitate here. If you keep on heating it, little by little, it will get darker and darker, and eventually you can observe the black color precipitate. When you are heating these solutions, be careful to not let the solution boil over. You have to keep heating it and taking it away from the heat, otherwise it will boil over and come out of the test tube, or you will see the solution gets splashed out of the test tube. So to avoid that from happening, make sure that you heat it gently, and as you observe that the solution is boiling, you can remove it from the heat and you can continuously boil it over a period of time, making sure you don't allow the solution to boil over. Now, students, you can observe that the precipitate has turned black. We can very clearly observe the precipitate that is formed over here is getting collected at the bottom, and you can observe what we have formed over here is a black color precipitate. So this black color precipitate is lead sulfide, and this was formed by taking our lead thiosulfate precipitate and heating it. So as we added lead ions and thiosulfate ions together, we formed lead thiosulfate, and when we heated our white color lead thiosulfate precipitate, we formed this black color lead sulfide precipitate. So what we have formed here is our black color lead sulfide precipitate. If you want to observe the color very clearly, I can bring it to the heat again. You can see as the solution is starting to boil, the black color precipitate will get suspended in the aqueous medium a bit more, and you can observe the color of the precipitate very clearly. And what we have formed here is a black color precipitate, which is lead sulfide, and we formed it by heating our lead thiosulfate white color precipitate. Now, let's go over the methods that we used to identify the presence of thiosulfate ions. First test we did was taking a sample of thiosulfate ions and reacting it with a mineral acid such as hydrochloric acid. When we add hydrochloric acid to a thiosulfate ion solution, we observed the formation of solid sulfur and sulfur dioxide. The formation of solid sulfur was clearly visible because solid sulfur, when it is getting formed in aqueous medium, it will be formed as a white color or yellowish white color precipitate. Solid sulfur is going to be produced in the form of colloidal sulfur. So the solid sulfur that is produced is going to be observed as a yellowish white precipitate. So we knew when we added hydrochloric acid to thiosulfate ion solution, sulfur is getting produced. Apart from that, we had to test for the presence of sulfur dioxide. So when we added hydrochloric acid to thiosulfate ion solution, sulfur and sulfur dioxide both were produced. To test for the sulfur dioxide that is produced, we sent the gas that is produced through acidified potassium dichromate and acidified potassium permanganate. Acidified potassium dichromate changes color from orange to green, indicating that there was a reduction in the dichromate ion from dichromate to chromium 3 plus. While this reduction was taking place, sulfur dioxide got oxidized to sulfate ions. When you send sulfur dioxide through potassium permanganate that is acidified, we saw the purple color of acidified potassium permanganate changing from purple to colorless. KMnO4 or permanganate ion, MnO4 minus ion, was converted from permanganate to Mn2 plus. Mn2 plus ion solutions are colorless, and that is the observation that we make. Purple color permanganate ion solution turns colorless as sulfur dioxide get oxidized to form sulfate. So these are the observations you make in the first experiment that was conducted to identify the presence of thiosulfate ions. And then afterwards, we moved on to reacting our thiosulfate with silver nitrate and lead acetate. When silver ions come into contact with our thiosulfate solution, we observed it forms a white color silver thiosulfate precipitate, which is an unstable precipitate, so it readily undergoes decomposition to form silver sulfide, which is a black color precipitate. And then we reacted our thiosulfate ions with lead 2 plus ions to form lead thiosulfate. Lead thiosulfate is a white color precipitate. However, if you heat the precipitate that is formed, you see that lead thiosulfate gets converted into lead sulfide, which is a black color precipitate. So the white color lead thiosulfate precipitate gets converted into a black color lead sulfide precipitate when you heat it. So that was our final observation, forming the black color lead sulfide precipitate. So after that observation, we actually conclude all of the tests that we can do to identify the presence of thiosulfate ions in aqueous medium. Now, let's move on to the next part of this experiment, where we observe what type of experiments can be done to identify the presence of nitrate and nitrite ions. Now, students, we are going to observe what will happen when we take nitrate ions and nitrite ions and react them with acidified potassium dichromate and acidified potassium permanganate. So over here we have 4 test tubes, and 2 of these test tubes are labeled nitrite ions and other 2 are labeled with nitrate ions chemical symbol, nitrate ions formula. So this test tube, we have nitrate and then nitrite. We have nitrate and nitrite formulas written here on these labels. Now, to 2 of these test tubes, we have taken acidified potassium dichromate, which are yellow color solutions, as you can see here. And to the remainder of the 2 test tubes, we have taken acidified potassium permanganate, which are purple in color. And to each of these test tubes, we will be adding a nitrate ion solution and a nitrite ion solution. Now, we have our nitrite ion solution here and the nitrate ion solution. Let's take this test tube. You can see it is labeled nitrite ions, and we have in this test tube acidified potassium dichromate, and to this test tube we will be adding nitrite ion solution. So let's add a few drops of nitrite ions solution here. Do you observe any change here? The answer would be no. Acidified potassium dichromate is an oxidizing agent. And can you further oxidize nitrite ions? The answer to that would be no. So therefore, in the presence of acidified potassium dichromate, you can't further oxidize nitrate ions. So therefore, there will be no reaction here and you will not observe a color change. Now, let's take acidified potassium permanganate and add to it a small amount of nitrate ions solution. Do you observe a color change? The answer would be no. In the presence of an oxidizing agent such as acidified potassium permanganate, nitrate ions can't get further oxidized. So therefore, you will not observe a color change as you normally would when it comes to acidified potassium permanganate. If acidified potassium permanganate is reacted with something that can get oxidized, acidified potassium permanganate will change its color from purple to colorless. And you will not see that observation here as nitrate ions cannot be further oxidized. Now let's move on to nitrite ions. So we have our nitrite ion solution here, and we have a test tube that has acidified potassium dichromate in it, labeled nitrite ions. Now observe what happens when we add a few drops of nitrite ions to acidified potassium dichromate solution. You can see it is gradually changing its color. And you can now observe it is green in color. So now, students, you can observe that when we added nitrite ions to acidified potassium dichromate, we have formed a green color solution. Earlier on, the acidified potassium dichromate was orange in color, but now you can very clearly observe the green color solution that we have formed. What has happened here is when nitrite ions are present in the medium, they can get oxidized by a strong oxidizing agent such as acidified potassium dichromate. So as they get oxidized into nitrate ions, you will see the dichromate ions get reduced to form chromium 3 plus ions, and chromium 3 plus ions along with water ligands and sulfate ligands that are present in the aqueous medium will form a green color complex, and that is why we observe the green color solution that we observed earlier. Now let's move on to our acidified potassium permanganate solution that we have here. To that, we can add a small volume of nitrite ion solution. You can see as we add nitrite ions, the color of the solution changes gradually and turns colorless. It's very clearly seen here. Now, if I mix this solution, you can very clearly observe the solution turning colorless. So students, this is due to acidified potassium permanganate being a very strong oxidizing agent. It oxidizes the nitrite ions, and as it oxidizes the nitrite ions, acidified potassium permanganate gets reduced to form Mn2 plus ions, which are colorless in aqueous solutions. So we can observe now, so a green color solution was formed when nitrite was reacted with acidified potassium dichromate, but with nitrate ions we did not observe any color change. We can see the orange color of the dichromate remained. Similarly, when we reacted acidified potassium permanganate with nitrate ions, we did not see any color change. It remained purple. However, when nitrite ions were reacted with acidified potassium permanganate, we observed how the color is changing. So purple color changed to a clear solution. So this indicates that when you are reacting nitrite ions, you will see nitrite ions are capable of getting oxidized to form nitrate, and if you are using oxidizing agents such as acidified potassium permanganate or acidified potassium dichromate, they will change their color. So this particular experiment can be used to separately identify between nitrate ions and nitrite ions. Now let's move on to the next test. Now students, we are going to be carrying out a very specific test that we can conduct for the identification of nitrate ions, and this test is referred to as the brown ring test. So for this test we will need a saturated solution of FeSO4, or in this case we have ammonium ferrous sulfate. We will need Fe2 plus ion solution, that is why we will be making a saturated solution of ammonium ferrous sulfate to obtain Fe2 plus ions, and then to it we will be adding nitrate ion solution, and then after mixing these two solutions together we will be adding concentrated sulfuric acid along the walls of the boiling tube that we will be using for this experiment. So as we add sulfuric acid along the walls of this boiling tube, since concentrated sulfuric acid is high in density, sulfuric acid will sink to the bottom of the boiling tube while keeping our Fe2 plus and nitrate ion solution on the top layer. And where the two layers meet, there will be a reaction taking place, and you will see a brown color ring forming. So in the presence of sulfuric acid, Fe2 plus and NO3 minus, you will observe a small reaction taking place where Fe2 plus is getting oxidized to Fe3 plus, while NO3 minus turns into nitric oxide or NO. So Fe2 plus ions that are present in the medium and NO molecules that are formed along with water ligands will form a brown color complex, and that is what we observe as the brown ring that forms at the interface between the sulfuric acid layer and Fe2 plus and nitrate ion solution layer. So let's move on to this reaction and observe the formation of this brown ring. In order to start our reaction, we will need a saturated solution of Fe2 plus ions. So to produce this, we will be using ferrous ammonium sulfate or ammonium ferrous sulfate that we have over here. We are going to take a small sample of ammonium ferrous sulfate into a boiling tube. So now let's add some water to this with the use of our wash bottle here. We'll add only a small amount of water because we intend to form a saturated solution of ferrous ammonium sulfate. You can see it is still not fully dissolved. We can add a bit more water. We can still see some solid remaining at the bottom, indicating that this is a saturated solution. We'll add a little bit more water and then proceed to add nitrate ion solution to this. So students, the importance of making Fe2 plus ion solutions freshly over here is there because Fe2 plus ions will undergo oxidation if you leave it out for a while and turn into Fe3 plus ions. So whenever you are conducting this experiment, you have to make sure that you freshly prepare your Fe2 plus ion solution. So this is still a saturated solution. There's a small amount of solid still undissolved here. We are going to take a small portion of this solution into a boiling tube that we will be using to conduct this experiment. And to this boiling tube, we will be now adding nitrate ion solution. We have our nitrate ion solution here. We will be adding about 2 cubic centimeters of nitrate ion solution to this boiling tube. After preparing our Fe2 plus aqueous ion solution and transferring around 3 cubic centimeters into a different boiling tube, we are going to place this in a cold water bath or ice water bath to cool down, as when you are making this first solution mixture, you have to make sure that Fe2 plus and nitrate ion solution mixture is cooled before adding sulfuric acid. So by cooling down the Fe2 plus aqueous ion solution mixture, and as it cools down, we can take our nitrate ion solution that we have here, and we can add about 2 cubic centimeters of nitrate ions solution to this Fe2 plus aqueous ion solution that we have here. And the solution is now somewhat cold, so we can add our nitrate ions solution to this boiling tube as well. After mixing the two, we can keep it placed inside the ice water bath for a while, and until it gets ready, we can prepare to add concentrated sulfuric acid. We can prepare to add concentrated sulfuric acid to this reaction mixture that we have here. Now students, when you are adding the concentrated sulfuric acid to this reaction mixture, you have to make sure that you add the sulfuric acid along the wall of the boiling tube that we have here. And you have to make sure to add a bit of a thick layer of sulfuric acid into this boiling tube. Otherwise, you will not very clearly observe the formation of the brown color ring that is getting formed. And if you shake the boiling tube while you add sodium hydroxide, you will not observe the formation of this brown color ring. The top layer will completely turn brown instead of forming a nice brown colored ring in the interface of sulfuric acid and Fe2 plus and nitrate ion solution mixture. So now we have allowed this solution to cool down for a while. We can now proceed to add sulfuric acid to this boiling tube, and when we are adding sulfuric acid, we are going to make sure we add it in such a way that it is running down the wall of the boiling tube. So let's take our reaction mixture here along with sulfuric acid, and we will take care to add sulfuric acid along the wall of the boiling tube little by little. Now students, what we did in this experiment was making a reaction mixture where Fe2 plus ion solution was added with nitrate ion solution, and we initially formed Fe2 plus and nitrate ion solution and we cooled it down, and afterwards we poured sulfuric acid, concentrated sulfuric acid, along the wall of the boiling tube, and without disturbing the top layer, sulfuric acid dropped to the bottom of the boiling tube, as sulfuric acid or concentrated sulfuric acid was denser. So at the interface where these two solutions meet, we can see the formation of a brown color ring. This is due to formation of a complex. Fe2 plus ions get oxidized into Fe3 plus ions, while the nitrate ions in the aqueous medium that we have here on the top layer get reduced to nitric oxide, or in other words NO. So the NO in the medium along with the excess Fe2 plus ions in the medium will form a complex. With one NO, there will be 5 water ligands connecting to Fe2 plus ions, forming a brown color complex, and that is why at the interface we have formed a brown color ring here. So we can very clearly observe this brown ring over here. If I keep it down on the table, you can see how at the interface we have formed a brown color ring. So this is referred to as the brown ring test for nitrate ions. This is a very specific test that can be done to observe the presence of nitrate ions with the use of Fe2 plus aqueous ion solutions and concentrated sulfuric acid. So what will happen if I shake this? They very clearly mentioned don't heat this or don't shake this, then this brown ring will disappear. So now I'm going to shake this. You will observe what will happen when I shake this mixture. You can see then the entire top layer is going to turn brown. So to avoid this from happening, we ask not to shake this mixture so that we can very clearly observe the brown ring that is formed at the interface between sulfuric acid layer and the aqueous Fe2 plus nitrate ion layer. If you continuously stir it, we can see that the color completely disappears as sulfuric acid completely reacts with the remainder of the aqueous solution. So now students, with that observation, we have completed yet another test that we can do to identify nitrate ions. So let's go through what we did in this experiment. We initially prepared a saturated Fe2 plus ion solution by dissolving ammonium ferrous sulfate in water, and we have to make sure that we always freshly prepare Fe2 plus aqueous ion solutions like this. Otherwise, Fe2 plus ions on standing can turn to Fe3 plus ions due to oxidation in air. So we will not be able to observe this brown ring test if you are using an old Fe2 plus aqueous ion solution. You have to freshly prepare your Fe2 plus aqueous ion solutions. After preparing the first Fe2 plus aqueous ion solution, we cooled it, and then we added nitrate ion solution to it. Afterwards, we very carefully added sulfuric acid along the wall of the boiling tube, and since concentrated sulfuric acid we added had a higher density, it sank to the bottom, and where the two layers meet at the interface, we saw a reaction happening that produced a brown color complex. At the place where the two layers meet, we saw Fe2 plus converts into Fe3 plus, while nitrate ions turn into nitric oxide, and this nitric oxide and the excess Fe2 plus present in the medium along with water forms a complex that is brown in color. That is why we observed a brown color layer where the two layers meet at the interface. So this is referred to as the brown ring test, which is a very specific test that can be done to identify the presence of nitrate ions. Now let's move on to the next test. Now students, we are going to observe an identification test that can be conducted to identify the presence of both nitrate ions and nitrite ions. So this test can be used to identify both nitrate and nitrite ions. That means you can't use this test to identify between two solutions of nitrite and nitrate ions, because this particular test that we are about to do actually answers to both nitrate ions and nitrite ions. So in this experiment we are going to be using aluminium powder, or pieces of aluminium can be used for this experiment. Zinc powder can be used for this experiment, or there's another alloy that is referred to as Devadas alloy, which can be used for this experiment. Out of these three options, we have aluminium powder here, and we are going to be conducting this experiment with aluminium powder. First, in this experiment, we are going to take to these two test tubes that are labeled nitrite ion solutions and nitrate ion solutions. So over here, to this test tube, we will take a small sample of nitrite ion solution, and to this test tube, we will take a small sample of nitrate ion solution. And then to it, we will add a little bit of aluminium powder. Afterwards, we will gently add sodium hydroxide. We will add small quantity of concentrated sodium hydroxide to each of these test tubes. Now, as you add sodium hydroxide, aluminium gets oxidized to form sodium aluminate. So aluminium goes from 0 oxidation state to +3 oxidation state, forming sodium aluminate, or in the presence of excess sodium hydroxide, it forms sodium aluminate. So as aluminium gets oxidized, you will observe that the nitrate ions or the nitrite ions, they get reduced to form ammonia. So aluminium get oxidized to form aluminate ions, and nitrate and nitrite ions get reduced to form ammonia. And we can test the presence of ammonia with the use of a wet red litmus paper and with the use of a Nessler reagent soaked filter paper. So we have both of them in front of us. We have two pieces of filter paper as well as red litmus paper. We are going to use them to identify the presence of ammonia that is released when we add sodium hydroxide and aluminium to each of these nitrite ion solutions and nitrate ion solutions. So let's first take two petri dishes and prepare our filter papers first. So we have Nessler's reagent here. We'll add a little bit of Nessler's reagent onto one petri dish. And as we start the reaction, we are quickly going to soak one filter paper with Nessler's reagent, and we are going to hold it over the ammonia gas that is released. And then later on, we are going to take a red litmus paper, and we have now taken a little bit of distilled water into another petri dish. So we will take a red litmus paper that you can see over here. We'll take this red litmus paper, quickly soak it in a little bit of water, and then we will hold it against the ammonia gas. So you can observe the red litmus paper turning blue in the presence of this ammonia gas that is produced. So let's first take aluminium powder into our test tubes. So we will take a small amount of aluminium powder into our test tube. This is mixed with pieces of aluminium as well. We'll do the same to the test tube labeled nitrate ions as well. Later on, we'll be adding nitrate ion solutions to this test tube. Now we have taken aluminium pieces and a bit of aluminium powder to this test tube as well. Now let's place this aluminium powder bottle over here, and we can now take a small volume of nitrite ions first, and then we can add this nitrite ions solution into our test tube labeled nitrite. So let's add a small sample of nitrite ion solution to this test tube. Now, as you can see, this is a metal that doesn't react with a solution of nitrite ions. However, it will react with concentrated sodium hydroxide. Now, after adding our nitrite ion solution to aluminium, we will place it here, and we are going to be adding concentrated sodium hydroxide to this reaction mixture we have. So as soon as we add sodium hydroxide, ammonia gas will be produced, and we are going to use a piece of filter paper dipped in Nestler's reagent. So we have on a petri dish here a little bit of Nestler's reagent. So we are going to soak this filter paper with Nestler's reagent. As you can see here, you can observe the color. We have this filter paper soaked in Nestler's reagent here in this petri dish, and I'm going to take a red litmus paper, make it wet with a little bit of water, as you can see here, and we will leave this red litmus paper here also on the side. So as ammonia gas is produced, we are going to use these two filter paper and the red litmus paper to confirm the formation of ammonia gas. So now let's take our concentrated sodium hydroxide solution we have here and add a few drops of, or we can add a little bit of sodium hydroxide to this, and when you mix it, you will observe after a while you will observe the formation of a gas here. So at that point, we will bring the filter paper that is soaked in Nestler's reagent over the mouth of our test tube and observe how the filter paper is changing its color. So as you can see, when gas is formed here, aluminium pieces are moving up as gas bubbles are getting attached to these aluminium pieces. So this indicates that gas is formed here. So now let's hold our filter paper soaked in Nestler's reagent over the mouth of this test tube to observe if there is going to be a color change. Now you can see, students, as ammonia gas is produced, the piece of paper that is soaked in Nessler's reagent is changing its color to a brown color. As you know, Nessler's reagent is used to identify the presence of ammonia or ammonium ions in an aqueous medium. Now, students, you can observe, as you can see, the filter paper soaked in Nessler reagent has now changed its color. It's very clearly a brown color. We did not start with this color, but now it is a very clearly a brown color. This ammonia gas that is produced is exposed to the Nessler reagent, and therefore it has changed its color to a brown color. Now let's take a red litmus paper and observe what happens. Now we have made the red litmus paper a little wet. Let's insert the red litmus paper and expose it to the ammonia gas that is released. You can see it is changing its color to a blue color. Let's observe that change one more time. Let's take another filter paper, soak it in water, and now let's insert it into this test tube, and you can observe, due to the exposure to the gas that is being produced, it is turning its color to a blue color. This indicates the gas that is produced is basic, and the Nessler reagent turning brown indicated that the gas that is produced is ammonia. So students, this indicates that we have in fact produced ammonia, and we can very clearly see ammonia gas being produced here when we mix aluminium powder with nitrite ions, and when we add concentrated sodium hydroxide to it, a reaction happens where ammonia gas is produced. So now we'll keep it aside and we can move on to our nitrate ion solution reacted with aluminium. So let's take a small volume of nitrate and to it we can add small amount of concentrated sodium hydroxide. And after a while, you will observe the formation of ammonia gas. Now students, you can see when we react nitrate ion solutions with aluminium and concentrated sodium hydroxide, we produce a gas here. Let's test if it is in fact sodium hydroxide. Let's take a filter paper soaked in Nessler's reagent, and let's hold it over our test tube. If it is in fact ammonia, this filter paper soaked in Nessler's reagent should turn to a brown color. As you can see, the filter paper soaked in Nessler's reagent is turning to a brown color, indicating that this is in fact ammonia gas that is released when this reaction is taking place. So this indicates that we have produced ammonia gas. And we can further observe that if you take a piece of red litmus paper, soak it in water, and if you insert this red litmus paper, you can observe it turning blue. So a red litmus paper will turn blue when exposed to ammonia gas. So that is why we observe this red litmus paper turning blue. We can observe it one more time. We'll take a red litmus paper that is are soaked in water, or that is made wet with water, and if you insert it over here, you can see the red litmus paper will turn blue. This indicates that the gas that is released is basic. So students, we saw how both nitrite ion solutions and nitrate ion solutions are going to react with aluminium powder and sodium hydroxide and produce ammonia gas. The same reaction can be observed if you take zinc powder and react it with sodium hydroxide and nitrate or nitrite ion solution. At that point, zinc metal will get oxidized to form zincate ions, or if you use sodium hydroxide as the base, zinc will get converted into sodium zincate, producing ammonia gas from nitrate or nitrite ions. The same observation can be made with the Devada alloy as well. This alloy is made out of aluminium, zinc, and copper. This alloy will also give you the same results if you experiment with the alloy using nitrate or nitrite ions. Now students, with this observation, we conclude the tests that can be done to identify the presence of nitrate and nitrite ions. Let's take a look at all the identification tests that we conducted for nitrate and nitrite ions. Later on, we observed if you try to oxidize nitrite ions with the use of strong oxidizing agents such as acidified potassium permanganate or acidified potassium dichromate, nitrite ions can get oxidized further to form nitrate ions. So therefore, the colors of potassium dichromate will change from orange to green, and colors of potassium permanganate solutions will change from purple to colorless. However, nitrate ions cannot get further oxidized. So if you react nitrate ions with acidified potassium permanganate or acidified potassium dichromate, you did not observe a color change. And then we conducted a very specific test for nitrate ions, which is known as the brown ring test. In this test, we made a fresh solution of Fe2 plus aqueous solutions and then reacted it with NO3 minus or nitrate ions. In the presence of sulfuric acid, we saw that Fe2 plus turns into Fe3 plus, while nitrate ions get reduced to form nitric oxide. So nitric oxide along with 5 water ligands form a complex with Fe2 plus ions that are brown in color. And we saw in the aqueous layer, we saw aqueous layer and sulfuric acid we added were present as 2 separate layers due to higher density of concentrated sulfuric acid. And at the interface, we saw a brown color layer was formed. This is where the reaction takes place, at the interface between the 2 layers. So therefore, we can observe the formation of a brown color complex. If you shake this, we observed that the top layer first will turn to a full brown color, but if you mix the sulfuric acid really well, so that you form only one layer, we will observe that the entire solution becomes somewhat yellow in color. This is because all of the Fe2 plus in the aqueous top layer gets converted into Fe3 plus, and you can no longer observe the brown color complex that is formed. Afterwards, we came here and we conducted the experiment with aluminium powder and nitrate ions, and then we conducted the experiment with aluminium powder and nitrite ions reacted with sodium hydroxide. And we saw as sodium hydroxide is added, aluminium got oxidized from aluminate anion, and we saw nitrate or nitrite ions get reduced to form ammonia. And we can test for the released ammonia with the use of a filter paper soaked in Nessler's reagent. We know when ammonia is present, Nessler's reagent will turn to a brown color. We observe that ammonia turns Nessler's reagent to a brown color. With this observation we have here, the filter paper soaked in Nessler's reagent turned brown when we exposed it to ammonia gas that is released. And apart from that, we also confirmed that it was a basic gas that is released with the use of a red color litmus paper that is soaked in water. So it turns to a blue color, indicating that the gas released was a basic gas and is in fact ammonia. So these are the tests that you can do to identify nitrate and nitrite ions. Let's move on to identifying carbonate ions. Now students, we are going to observe the identification test that we can do for carbonate ions. As you know, when you take a solid carbonate and react it with an acid, you will form carbon dioxide gas. So over here we have sodium carbonate today, and we will be adding dilute hydrochloric acid to this sodium carbonate we have here, and as hydrochloric acid reacts with the sodium carbonate, it will produce carbon dioxide gas. So this is an identification test that we can do for carbonate ions. However, how do we identify the presence of carbon dioxide gas? Carbon dioxide gas, when sent through calcium hydroxide, which is also referred to as lime water will be turned milky. This is due to calcium hydroxide reacting with carbon dioxide to form calcium carbonate solid, which is a white color, water insoluble precipitate. But this solid is going to be formed in such fine particles. They distribute throughout the aqueous medium to form a milky solution. So let's take a small sample of our calcium or sodium carbonate here into our test tube, and then add a little bit of hydrochloric acid and observe the formation of carbon dioxide. Now we have taken a small sample of sodium carbonate here, and we are going to be adding hydrochloric acid to it. And as soon as we add the hydrochloric acid, we will place this rubber stopper connected to a delivery tube, and the produced carbon dioxide will be sent through lime water. So we have to take lime water to this test tube that we have here. We have our lime water solution here. Let's take a small sample of lime water to this test tube. As you can see, lime water is a clear solution. It is not in any way a milky solution. It is a clear solution. So when we send carbon dioxide through this, you will observe this lime water turning milky. So let's place that test tube over here, and we can insert the delivery tube into our lime water solution and proceed to add our HCl to our sodium carbonate solid we have here. Now students, as soon as we add our HCl, we have to close the stopper, otherwise carbon dioxide produced will be released out of the test tube, so you will not observe the lime water turning milky. So as soon as you add the HCl, make sure to place the stopper and close the test tube. Now students, you can observe, as I added hydrochloric acid to the carbonate, we produced a gas, and that gas was delivered through this delivery tube into lime water, and lime water turned milky. Lime water earlier was clear. Now you can observe that it is milky in nature. So now what we can do is we can continuously send more and more carbon dioxide through this and observe how this milky color will disappear. Let's take a bit more hydrochloric acid and we'll add this acid to this test tube. And we'll continue to send carbon dioxide through this lime water solution. You can see now the lime water initially is increasing its color, maybe because there was more calcium hydroxide that did not form calcium carbonate. So to observe lime water turning clear, we can take another test tube and take a small portion of this solution into that test tube. And to make this reaction happen a bit faster, we can dilute this suspension that we have over here. Now we have a diluted version of this milky solution we have here. What we have here on the right hand side is a diluted suspension of this milky suspension I have on the left hand side. So now we will send carbon dioxide through this diluted milky suspension we have and observe how it turns clear. Did you observe that milky solution completely turned clear when carbon dioxide was sent through it? Did you observe how it turned clear when carbon dioxide was sent through it? So if you want to observe it one more time, we can take a dropper and add a small amount of this milky solution again into the solution over here, and you can see now the solution is a bit milky. And when you send the carbon dioxide through this milky solution, let's observe how it turns clear. We can very clearly see that this solution has turned clear as well. So we'll take the last portion also and we'll try an attempt to make it clear as well. We'll add a little bit of HCl. We can see even that solution is turning clear little by little. Earlier there was a very strong milky color, but after a while we can observe it turning clear. We'll add a little bit more HCl. Now students, we can very clearly see when we are sending more and more carbon dioxide through our milky calcium hydroxide solution, it is turning clear once more. This is because when carbon dioxide is sent through calcium hydroxide, initially it forms calcium carbonate, which is a water-insoluble white color precipitate. And this white color precipitate is suspended throughout the aqueous medium, making the lime water milky. But when you send more and more carbon dioxide, this calcium carbonate turns into calcium bicarbonate, which is a water-soluble compound. So that is why the lime water that was milky will be turning back again to a clear solution when you send excess amount of carbon dioxide through the milky lime water. So now we have observed the reaction that we can use to identify the presence of carbonate ions as well as carbon dioxide gas. Let's move on to the identification of hydroxide ions. Now students, as an additional experiment, we are going to observe how we can identify the presence of hydroxide ions with the use of aluminium 3+ ions, zinc 2+ ions, or magnesium 2+ ions. So we have over here aluminium chloride. We can take a small solid sample of aluminium chloride into a test tube. And after taking a small solid sample of aluminium chloride, we can dissolve it by adding a little bit of distilled water. As you can see, when it dissolves, it forms a clear solution. And now students, we are going to take a small volume from this original stock sample into a separate test tube. And we are going to add a very small amount of dilute sodium hydroxide. So when you add sodium hydroxide to aluminium 3+ ions, what do you think will happen? Let's observe first. As you add sodium hydroxide to aluminium 3+ ion solution, we can see the formation of a white color precipitate. What is this precipitate? This is aluminium hydroxide. Aluminium hydroxide is an amphoteric hydroxide, meaning if you take a small sample of this aluminium hydroxide suspension and react it with hydrochloric acid, it will dissolve in hydrochloric acid. And it will also react with excess sodium hydroxide and dissolve in excess sodium hydroxide as well. So this aluminium hydroxide white color precipitate that we have over here is an amphoteric hydroxide. So let's observe how it reacts with hydrochloric acid. So we have HCl here. Now let's add a little bit of HCl. You can see as few drops of HCl is added, the white color precipitate completely disappeared as it dissolves in HCl. We can add a bit more HCl. We can now see the precipitate completely disappeared when we added HCl to our aluminium hydroxide precipitate that we formed earlier. To the second sample, we are going to add a small volume of concentrated sodium hydroxide. Let's take our concentrated sodium hydroxide reagent bottle here, and with a new dropper, we will add a few drops of concentrated sodium hydroxide to observe what takes place. You can see as a few drops of concentrated sodium hydroxide is added, the aluminium hydroxide precipitate that we observed started to dissolve in it. So let's shake this and observe what happens. As you can see, when we shake the solution, the sodium hydroxide further reacted with aluminium hydroxide and dissolved the aluminium hydroxide in excess sodium hydroxide. Over here, aluminium hydroxide turns into sodium aluminate. Aluminium hydroxide turns into aluminate anion, and along with the sodium ions in the medium, it forms sodium aluminate. So the aluminium hydroxide precipitate that we observed earlier was an amphoteric hydroxide that dissolves in both hydrochloric acid as well as excess sodium hydroxide. So this is a test that can be used to identify the presence of hydroxide ion. This test also can be used to identify the presence of aluminium ions. However, apart from aluminium ions, zinc 2+ ions will also behave the same way. When you add hydroxide ions to zinc 2+ ion solution, you will see the formation of zinc hydroxide, a white color precipitate. However, zinc hydroxide will react with further or excess sodium hydroxide to form sodium zincate, which is a water-soluble substance. So therefore, the precipitate that is formed will disappear. And at the same time, zinc hydroxide will react with acid as well to form a clear solution once more. So therefore, students, you will observe a similar reaction with zinc 2+ ions as well that can also be used to identify the presence of hydroxide ions. Now, we can move on to magnesium nitrate. We have our magnesium nitrate solid sample here. We can use a new spatula to take a small amount of magnesium nitrate into a new test tube. And now we can dissolve this magnesium nitrate with the use of distilled water. You can see magnesium nitrate dissolves well in water. We can add a little bit more water to dissolve all of the magnesium nitrate that we have here. After forming our magnesium nitrate aqueous solution, we are going to add a few drops of dilute sodium hydroxide, and you can observe as we add sodium hydroxide, you form magnesium hydroxide, which is not soluble in water. You can see a white color magnesium hydroxide precipitate is formed and it is suspended in the aqueous medium. We can add a few more drops of sodium hydroxide. You can see magnesium hydroxide is formed. Magnesium hydroxide is a white color, water insoluble precipitate. And this magnesium hydroxide suspension is going to be separated into two different test tubes. And to test whether magnesium hydroxide is an amphoteric hydroxide, we are going to first add it with HCl. So let's observe whether magnesium hydroxide dissolves in hydrochloric acid. You can see as HCl is added, the white color magnesium hydroxide precipitate is starting to dissolve. Now if I mix this suspension really well, it will come into contact with the HCl really well and dissolve all of the magnesium hydroxide that we had in this test tube. And if you take the second magnesium hydroxide suspension sample we have here and add concentrated sodium hydroxide to it, we have our concentrated sodium hydroxide here. If you add concentrated sodium hydroxide to it, let's see what happens. Do we see that the magnesium hydroxide is dissolving in concentrated sodium hydroxide? Actually, the precipitate just increased because there were some magnesium 2 plus ions that didn't react earlier with the hydroxide ions because we didn't introduce enough hydroxide ions into the medium. But when we added more and more concentrated sodium hydroxide, we see that magnesium hydroxide that is produced is not dissolving. Instead, excess magnesium 2 plus ions that were present in the medium will start forming more and more magnesium hydroxide white color precipitate. So magnesium hydroxide is not an amphoteric hydroxide. In fact, magnesium hydroxide only reacts with hydrochloric acid and it dissolves in hydrochloric acid but not in excess sodium hydroxide. So we observed if you take aluminium 3 plus ions, when you add sodium hydroxide to it, it will produce a white color precipitate. However, if you take a small sample of this aluminium hydroxide, white color precipitate, and add concentrated sodium hydroxide, we observed how it dissolved in concentrated sodium hydroxide, indicating that aluminium hydroxide was in fact amphoteric hydroxide. So what we have formed here is sodium aluminate. What will happen if we add HCl and acidify the medium once more? You can see as we acidify the medium once more, we form aluminium hydroxide again. And if you add enough and more HCl, this formed aluminium hydroxide will again dissolve to form a clear solution. As you know, aluminium hydroxide is soluble in HCl. So let's observe that as well. We'll transfer some to another test tube so that we only have a small volume to handle here. So now we are going to continuously add HCl, and you can see as more and more HCl is added, that produced aluminium hydroxide dissolved completely in the HCl that we added into the medium. So this very clearly indicates that aluminium hydroxide is an amphoteric hydroxide. Now students, we observed two main experiments in this particular part of our experiment. We saw hydroxide ions can be identified with the use of aluminium 3 plus ions or zinc 2 plus ions. Both of them will produce a white color metal hydroxide that is insoluble in water. Upon the addition of HCl, these hydroxides will dissolve. However, upon the addition of excess sodium hydroxide, we saw they will also dissolve to form a clear solution. Aluminium hydroxide will dissolve in excess sodium hydroxide to form sodium aluminate. It will also dissolve in HCl. Apart from that, zinc hydroxide will also dissolve in excess sodium hydroxide as well as HCl. In excess sodium hydroxide, it will form zinc, it will form sodium zincate. Apart from that, we observed how magnesium hydroxide is only reacting with the acids and not with excess sodium hydroxide. Students, that will be all for today's experiment. With this, we conclude experiment 11, identification of anions.